chair of CITAC. And this is in fact the second time that we do this celebration as a web seminar in an online form. So this is something that in the past used to be part of our annual meeting, usually in Paris. And now, since we have the COVID pandemic, we have changed that. And starting last year, we are celebrating this as a web seminar. And it gives us the nice opportunity to also invite a further audience from other parts related to metrology and chemistry to this kind of CITAC Best Paper Award ceremony. And it's very nice to have a wider audience here that comes to us and celebrates with us. So a very warm welcome to all of you. So the program for today will be that I give to all those who are not usually with us a brief introduction about CITAC. And in the second stage, I would like to pass it on to Zoltán Mester, who is our vice chair and responsible person for the CITAC Best Paper Award. And then we move on to the ceremony itself, and it is our past chair, Michaela Sega, which will guide you through the procedure. So welcome to all of you again. So I would now like to share my screen and want to show you a few slides about CITAC as indicated, and that should help you to become a little bit more familiar with CITAC and what we do. So just a minute for that. So you should be able to see my screen now, is that right?
Yes.
Yeah, perfect. So just move a little bit to the start. So CITAC is an organization that was founded in 1993. So back in those days, we did not have officially signed metrology and chemistry at the BIPM in Paris or as a part of the meter convention. And at that time, there was a strong movement to get international traceability in analytical chemistry as an integral part of all measurements which are carried out in the framework of the meter convention. So there was a gathering at a meeting in Gaithersburg that got this whole development started, which then resulted in the foundation of the consultative committee for the amount of substance, chemistry and biology at the meter convention that meets twice a year and once every year in Paris. Now, at this time, it was a collaboration of people who were interested in accurate measurements and traceability in analytical chemistry from all around the world. And they got together with a mission to establish traceability of the results of chemical measurements everywhere in the world, and to ensure the analytical measurements made it in different countries to be comparable at any place at any time. Now, there were several points that were raised together that everybody would like to follow on. And the idea was to facilitate the practical realization of metrological traceability in chemistry, and to develop concepts that can be applied broadly at analytical laboratories and to disseminate those concepts. So it should be something that's not only happening on the level of the meter convention and national metrology institutes, but all around, and should reach the general public and every user who is interested in chemical measurements and chemical measurements results and their quality assurance. It was also intended to collaborate. This was one of the things why these people got together, and to have a collaboration that was cross-cutting from metrology institutes down to every single laboratory that is involved, and to use joint principles and technologies for that purpose. The aim was to promote metrological principles in chemistry through guidelines and other tools for analytical laboratories. So the promotion of guides, the establishment and the promotion of guides together with other interested organizations is a key part of the activities of CITAC. So this included the promotion and the harmonization of quality practices in analytical chemistry laboratories, and to stimulate education and training on metrology and chemistry. So at least at that time, this was not part of the general curriculum of any university, and it was also the aim to introduce the concept of metrology and chemistry at these places, and also in industry and at other places, of course. Now, this was from the beginning on an international collaboration, as I said, and this is a distribution of the members that we have in this organization now. And you can see that there is a large activity in Europe, Asia, America, but also at other places in the world. And we welcome everybody who is interested in these activities to join us at CITAC. We can also see, as I said before, it is not just the NMIs who are interested and involved, but also many other people from academia, research bodies like universities and other research organizations, industries, and further organizations from everywhere in the world. So as I said before, one of the key activities of CITAC is a production and promotion of guidelines, and what you can see here on the right-hand side is one example for a new guide that is the second edition of the EURAChem CITAC guide, use of uncertainty information on compliance assessment. So the collaboration with EURAChem, as you can also see from the other guides that were already produced, is a very important and integrated part in the activities of CITAC. And the same applies to IUPAC, and we have also published several guides jointly with IUPAC, and this is an example for the last one that has been published. So further to this, IUPAC and CITAC and also other organizations have produced and carry out workshops, and these workshops used to be carried out in different parts of the world, and we still want to come back to that situation that we have had before, to have this worldwide distribution. But in the current pandemic, the situation has changed, of course, and we have also changed about these workshops and do it as a web seminar nowadays. And the first one of those was carried out in January 2021 on metrology, quality assurance, and chemometrics. This should have been in Israel. That was the original plan, organized by Kuselman. And we have, of course, now had this in a purely virtual form. So maybe next time we can also change back to a real workshop at a real place on Earth. But on the other hand, it gives us an opportunity, as I said before, to invite further people and have a broad audience. And in case of this workshop, these were actually more than 200 participants in this workshop. So we consider this as a big success, and we are very happy that we were able to carry it out in this form. Now, this is yet another web seminar, and now this time, as said before, on the CITAC Best Paper Award 2020, and we have some eminent people to talk about the work that they did, and the exceptional work that they did was therefore awarded with the CITAC Best Paper Award. And I'm very happy to welcome these people here to give us a little bit of insight into the work that they did, and so that we have a possibility to talk to them also about the work that they did. So in order to carry this procedure out now, I now pass on to Zoltan, our vice chair, and ask him to continue with the procedure. So I stop sharing my screen now. I hope I can do that easily. So here we go.
Good morning, everyone, or good afternoon, or good evening. I have only 2 slides.
You're a little bit far away, Zoltan. Can you speak up a little bit?
Hello.
Perfect.
Great. Welcome everyone to our annual award ceremony. In this year, I had the pleasure to run the CITAC Awards, which has been active for more than a decade and a half, with numerous highlighting numerous significant contributions to metrology and chemistry. The aim of the award is to highlight interesting papers published in previous year in the field of metrology and chemistry. The nomination is open to members of CITAC. The nominees, however, could be anyone active in this field. This year we have implemented an electronic nomination platform through SurveyMonkey, which is actually is already open for our next round of awards. So if you would like to scan the QR code or take note of the link below, this would be the nomination link where you can submit your papers or paper of interest for our next year's award. Without further ado, I would like to hand it over to Michaela.
Thank you, Zoltan. Thank you, Bernd, for the kind introduction. Good morning, afternoon, or evening to everyone, and thanks for joining in the CITAC Best Paper Award 2020 ceremony. I will try also to share my screen. Let's see if it works. I hope so. I hope you are able to see the screen, the presentation. So thanks for being with us for this ceremony. According to the agenda, after this introduction that we had, we move to the presentation of the 3 papers that have been awarded by CITAC for the year 2020. We will have, as in the previous edition of the ceremony, a presentation of 20 minutes each for each of the 3 papers, followed by 5 minutes of discussion. In case you have questions or comments on the presentations, or if you had the opportunity, that I hope so, to read the papers, please type your questions in the chat and they will be addressed during the discussion after the presentations. So let's start with the first presentation, which is on the paper entitled Correlation of Test Results and Influence of a Mass Balance Constraint on Risks in Conformity Assessment of a Substance or Material. When components of a substance or material are subject to a mass balance constraint, test results of the component contents are intrinsically correlated. This so-called spurious correlation affects measurement uncertainty and so may influence the understanding of test results and risk evaluation in conformity assessment. The present paper is the position paper of the IUPAC CITAC project, Influence of a Mass Balance Constraint on Uncertainty of Test Results of a Substance or Material and Risks in its Conformity Assessment, and it aims at developing a technique for appropriate evaluation of the risks. A Bayesian multivariate approach to evaluate the conformance probability of materials or objects and relevant risks discussed for different scenarios of data modeling, taking into account all observed correlation. The speaker is Dr. Francesca Pennecchi from INRIM, the National Metrology Institute of Italy. Please, Francesca, the floor is yours. I will stop sharing my screen as soon as I can. Okay, I think I'm done.
Okay, thank you, Michaela, very nice, very much for this nice introduction. And I will start sharing my video. Could you see it? I hope so.
Perfect.
Thank you very much. So first of all, I really would like to, from my side and on behalf of the co-authors of this paper, I would like to thank very much CITAC for this great recognition. We are honored to receive the award and very happy to have the possibility today to present our work that, as already said by Michela, is just a first paper from my whole IUPAC CITAC project I will be talking about. You can see here the pictures of my colleagues and also very good friends of mine, Aglaia Di Rocco from the University of Torino, and Ilya Kuselman, Brian Hibbert, and Michela Sega, who are also CITAC members. So, as already said, I will talk about the IUPAC project, of which paper is the revision paper. This project actually is a follow-up of a former project, and so I will mention a little bit also about that. And I think it's important to make a brief recap of the main concepts of conformity assessment of a single item and then of a multi-component material object to highlight how to move from particular to total risk and what they mean. We will see it. Then we will focus on mass balance constraint and compositional data, which are seen as a special case of multi-component material. And I will show how to adapt the Bayesian framework for conformity assessment to such kind of compositional data. The example of the paper is the study of a chemical composition of a platinum rhodium alloy seen as a compositional data. And finally, some conclusions. So the project I'm talking about has the title Influence of a Mass Balance Constraint on Uncertainty of Test Results of a Substance or Material and Risks in its Conformity Assessment. The project started in July 19 under the chairmanship of Ilya, with the collaboration of Brian Hibbert, Aglaia Di Rocco, and myself. And it deals with those cases where the components of a substance or materials are linked through a mass balance constraint. That is when the sum of their fraction, mass fraction or molar fractions has to be equal to, let's say 100% or 1, for example. In this case, the test results of such components content are named compositional data. These data are inherently correlated because of the mass balance constraint. And these induced correlations are called spurious correlation, which are a kind of a mathematical property of the data that are not related to any physicochemical interdependence between the components. So the main aim of the project was to model and to study the effect of the mass balance constraint on the conformity assessment of such substances material. The applications are several in very scientific field. And as mentioned before, this project, you can see here in the link all the papers and the updates of the project, is actually a follow-up of the project already mentioned by Bern in his introduction, that developed an IUPAC CITAC guide on the evaluation of risks for decision and conformity assessment of multi-component material or object. So before talking about multi-component material, it is important to recap some basic concepts of conformity assessment for a single item. We know that the conformity assessment is a demonstration that specified requirements relating to a product or a system are fulfilled. And we usually deal with tolerance interval and acceptance interval. The former is an interval of permissible values of a property of an item. The second are interval of permissible measured quantity values. Actually, we deal with two quantity. C is the true concentration value of an item that should be within the tolerance interval to be considered as good, so to be considered as conformant. But we cannot know C perfectly, our measurand, because of course we have measurement uncertainty to face with. So we have CM, that is the measured value of the item, the test result. And so we compare if this measured value is or not within the acceptance interval in order to make a final decision on the conformity of the item. For example, if the triangle is the measured item, and in this case it is outside the tolerance interval, you see the bar is the uncertainty bar, this item would be rejected. But if the true value is the square and the right square, we would make a false rejection. And this is linked to the producer's risk probability that a rejected item is conforming. The other way around, this is the consumer's risk, the probability that an accepted item instead is non-conforming. So the two good situations are these on the main diagonal, where both the measured value and the true value are within their respectively acceptance and tolerance interval, or at the same time they are outside. The other two situations are a false failure leading to the producer's risk and the missed failure, which is related to the consumer's risk. How to calculate these risks? We rely on the framework provided by the document 106 from the Joint Committee for Guides in Metrology, which is a Bayesian framework, a Bayesian approach, according to which knowledge about an item property, it is our measurand, can be treated and modeled as a random variable and expressed in terms of a probability density function PDF. So we have some prior knowledge that is modeled by this prior PDF. In some cases would be very vague, so it's not much important, but in other cases you may have some good prior knowledge to be combined together with the likelihood function, which is all the fresh information you acquire during the measurement process, so that the measurement certainty plays its role here in the likelihood function, which model the quality of your measurement process. Finally, through the Bayesian theorem, you get a posterior probability density function, which is all you can know about your measure at C, given that you have measured your test result CM. From this PDF, you can get an estimator or a coverage interval or a standard deviation taken as the certainty of your measurement to be associated to your result. For example, the conformance probability, that is the probability that an item fulfills the specified requirement by its definition, is nothing else the integral of this posterior PDF on the tolerance interval. Well, these are the main ingredients for calculating the risks. I mean, the posterior G, probability density function, and also the two, the prior and the likelihood, that put together, they form the joint PDF of the measured value CM and the true actual value C. The posterior, you can use it for calculating the specific risks, specific in the sense that they are related to a specific test result CM. Global risks are referring to the population as a whole. So our global risk in the sense that if you pick up at random one item from your population, for example, the producer's risk is the probability that the measured value is outside acceptance interval, so is rejected, but the actual corresponding true value is good, that is inside the tolerance interval. So you use the double integral of this joint PDF. So far we have considered just one item at a time, but what if we have multi-component material? A multi-component material or object is made of n components that can or cannot be correlated one to each other. In this case, we cannot just rely on the single risks for each single component. We cannot just work component by component, but we have to treat the multi-component object as a whole. In this sense, often when particular conformity assessment risks are acceptable, particular means for each component, the total probability of a false decision might still be significant. And this total means concerning the whole multi-component object, so taking into account all the n components together. Total comes from the use of the total law probability that we have used for addressing this issue from the probability point of view. So the multivariate Bayesian, the Bayesian approach become multivariate in the sense that the posterior, the prior, and the likelihood are all multivariated PDF now. And of course, C and CM are now vectors, because each one is made of n components. So I'm using the bold font here. For example, just to give you an idea, what is the total specific producer's risk? It means that at least one of the measured components, CEM, was not good, was outside its acceptance interval. So it is sufficient that one is bad and the whole object, the whole multi-component object is rejected, of course. But what if all the true C values were actually good? In this case, the object should have been accepted and not rejected. So this is the total specific producer's risk. That is, again, nothing else, in this case, a multivariate integral, multiple integral of the posterior PDF, calculated on the tolerance domain that is now a multivariate region, not just a single interval. So without entering the detail, what I want to convey is that we start from the component by component framework proposed by the Joint Committee for Guidance and Metrology, where for each component you can, of course, take into account the measurement certainty of each component, but we then move to total risks for multi-component material, in which you not only take into account the measurement certainty of each component measurement result, but also the correlation that could be possible among the measurement test result and the actual true value. This correlation could be metrological related, could have a natural source, for example, stoichiometry, or technological reasons by the characteristic of the production of those items, for example. And among those correlations, we have also as I said at the beginning, spurious correlation, which are typical of compositional data. So we come to the main topic of the composition paper, that is compositional data due to the mass balance constraint. So we give here a brief introduction. We said that a raw vector C is defined as n-part composition when all its components are strictly positive real number and they carry only relative information. The sample space of compositional data is called simplex, which is defined as the set of all those vectors whose components sum up to a certain constant, usually 1 or 10. So we are speaking of parts per unit or percent. Compositional data analysis theory has been developed since the 80s. It's a quite important topic in statistics, developed by its very pioneer, who is a Scottish statistician, John Atkinson. And since then, several examples of application have been developed in many fields, geochemistry, astrophysics, material science, and so on. This compositional data have plenty of property. The main on which we focus is the fact that the only information carried by a composition is provided by the ratio between its components. So it is natural to select a representative of this class of equivalence, and this is usually formalized by the closure operation, in which the single components are rescaled in a way to sum up to a constant K. The aim of these IUPAC approaches was to extend the Bayesian framework already developed for the multi-component materials to the data which are restrained to a mass balance constraint, which are actually a particular subset of correlated multi-component materials. Okay? So we used actually the same multivariate Bayesian framework, but we had also to take into account the mass balance constraint, so the sum of the components equal to, in this case, 100%, and the fact that all the components must be positively defined. The first step is to model the available information in order to associate appropriate probability PDF for the prior distribution. We know that according to the principle of maximum entropy, if you just know a mean value and a covariance matrix for your data, you assign a multivariate normal probability density function. But if you add some more information, for example, in our case, we know that the C values are all positive, the maximum entropy distribution is a truncated multivariate normal distribution with parameters mu and b And also, so for the prior PDF, we use this truncated multivariate normal distribution, but also for the likelihood function, for the same reason, you use the same family of distribution, and now the parameters are the true value, the actual true value C as the mean of the PDF, and the uncertainty matrix of the experimental result for the scale parameter. So this is just a couple of features of a univariate and a bivariate truncated normal distribution, truncated in 0. Let's see what we have done with specific cases. We considered an alloy of platinum rhodium made of 3 components, and the aim of modeling and calculating the total risks in the conformity assessment of such alloy as a multi-component material. Of course, the evaluation of this risk was important for understanding the quality of the product. The 3 components, perfectly compositional, were platinum, rhodium, and impurities, C1, C2, and C3. You can see here the tolerance limit provided by relevant standards. And you should know that the platinum, the first component, were obtained as 100% minus the other 2 measured value. So the first step, as I said before, is to assign a prior PDF based on the available knowledge. And we used as available knowledge a total of 100 batches of such alloy produced at the same plant during 2 years. The population mean and the standard deviation are reported here together with the Pearson correlation coefficients between the 3 components. And also the typical measurement uncertainty are reported. Note that the content of platinum has a negative correlation, you see this correlation, this one, both with the second and the third component, and this is due to the mass balance model for which the platinum is obtained as 100 minus C2 minus C3. So it is clear that we can have a negative correlation in this case. And also the uncertainty associated to the platinum is obtained applying the low propagation of uncertainty to the mass constraint model. Then, in order to model the multivariate prior PDF of the actual C values, we consider the 3 possible following models. Model 1. According to this model, we perform a simulation by drawing randomly the values from a multivariate truncated normal PDF with mean, mu, and covariance matrix V provided. These parameters were provided from the 100 batches. Okay? And then we perform the closure operation because we have to model the fact that the data are compositional. In general, this approach is suitable for materials whose composition is tested completely. That is, all its components are measured, and they have to satisfy the mass balance constraint. In model 2, we make a different choice. We assign again a multivariate truncated normal distribution, but just to the second and the third component, using the correlation we have between the 2. And then again, we obtain, we obtain now deterministically platinum C1 is equal to 100 minus C2 minus C3. This kind of model can be applied for pure substances or materials in which the main component content is not directly measured, but actually, as in this case, is calculated as 100 minus the other contents. We investigate also a third model, sequentially modeling, in which we model 1 component at a time. We start from the rhodium, to which we assign a univariate truncated normal. Then we assign a further truncated, univariate truncated normal to the impurities. And finally, again, the platinum was obtained as 100 minus the others. For these 3 models, we drew 10 millions of Monte Carlo values, and we calculated the correlation coefficients and the conformance probability. And we compare these values with the original one, the experimental ones, to see how these models could actually reflect the information we had from the 100 batches available. And you can see that experimental correlation are almost the same for model 1 and 2 with respect to the experimental, but you can see some differences in model 3, mainly for what concerns the this correlation that was 0.228, and here in model 3 it becomes 0. So what we can say the model 1 and 2 are essentially reflecting quite well the a priori knowledge. Instead, model 3 is just taking into account the spurious correlation, the correlation due to the truncation effect and to the mass balance constraint. This model, the sequential modeling, is not able to accommodate any other sources of correlation that could be natural, physicochemical, or technological. So this model is not well suited for cases in which there are other sources of correlation other than the spurious. But on the other hand, we have to say that it could be useful to apply it anyway, just in order to disentangling the spurious part from the total amount of correlation. So far we had modeled the prior, the probability density function. Now we move to the likelihood function. And here the modeling of the likelihood function follows conceptually the same as those considered for the prior. Now the main difference is that the covariance metrics is not those obtained by the 100 batches, but is the uncertainty, the experimental uncertainty covariance metrics. For each model, we drew 10 million of Monte Carlo simulation vector made like that, the 3 true values and the corresponding 3 measured value, okay, drawn according to the joint PDF we already have modeled. And we calculated the total global risk. In this way, among the 10 millions of simulated vectors, the consumer's risk was calculated as the fraction of cases when all the measured value were good, but at least one true value was not good, was outside its tolerance interval. The other way around, the producer's risk was the fraction of all those cases when at least one measured value was not good, but actually all the true C value were good. That was a numerical approximation of the two risks. And these are the results we obtained when considering an acceptance interval exactly equal to the tolerance interval. We get a total consumer's risk over 4.7 times 10 to the 3. The producer's risk was larger. And here we see again a slight difference between model 3 and model 1 and 2. We already discussed about the limitation of model 3. And then we were curious to see how these total global risk could vary with respect to the acceptance interval. So this is the surface of the total global risk when the acceptance interval for the rhodium A2 and for the impurities A3 varies. And this length of acceptance interval were made varying from the value of the tolerance interval up to 3 uncertainty far away. Okay, one can see in this example that the risks depend on the acceptance limit chosen for rhodium A2. So you see this decreasing. But is practically independent on what happens to the acceptance limit for the impurities. So in this case, the dependence was mainly on the acceptance interval relevant to the rhodium, to the second component. In general, this kind of plots allow to choose the proper acceptance limits, which correspond to a desired risk level for the consumer and the producer. So coming to our conclusion, in this project, we are adapting the multivariate Bayesian framework for conformity assessment to compositional data. We resort usually to multivariate truncated normal PDF for modeling prior and likelihood function. We considered the spurious correlation within, embedded in the covariance matrix used for prior and likelihood function. And we also modeled the mass balance constraint through our Monte Carlo simulations by means of appropriate closure operation. We already published other two case studies following the former, described here in this position paper, a case study on potassium iodide, considered as a potential reference material, and also a case study relevant to a food product. Now we are, at the moment, we are working on a case study of synthetic air and its conformity assessment, so relevant to particular gas mixture. So thank you very much, and if you have any question, please ask me. Thank you very much.
Thank you so much, Francesca, for your clear presentation. Are there any questions or comments? I didn't see anything in the chat. Is there someone who would like to pose a question to Francesca? Francesca, I saw that you are moving on with different examples on different scenarios and so on. Is there have you already thought about some additional fields where this kind of measure of study could be applied?
We at the moment, as I said, we are working, for example, on a sample, on a case study relevant to gas mixture that is also very important for reference, for producing reference materials. And the other two were for food control, and the other one for, as I said, potassium iodide, or considered as a potential reference material too. For the moment, we are concluding with these four examples for the project, and we have an idea to proceed with an IUPAC CITAC guide on this project, as we made for the multi-component material. It would be good also to provide a comprehensive guide also on compositional data and conformity assessment for compositional data. So for the moment, we will encompass these four examples within the guide, but of course, nothing prevents us to study other fields of application. So if anyone is curious also to, and is dealing with compositional data and mass balance constraint data, I encourage them to approach us, and we can see the examples are good to interesting to be treated with the framework we have been developed so far. So we also hope to be useful to other colleagues in case they want to address conformity assessment problem in their field of application.
Thank you so much, Francesca. Are there questions, any other questions or comments? If not, thanks again, Francesca. And
maybe I have a question, Michela.
Oh, yes.
Yeah, an obvious application for this purity assessment is, of course, nowadays the investigation of the purity of vaccines. So that's a thing that's widely discussed. The quality of the vaccines largely depends on their safety, on their purity. Would that be an application case?
Oh, yes, I think very, very useful. And for the moment, yes, it would be nice to investigate this problem of conformity assessment for vaccine. Why not? The problem, well, the fact is they should be compositional in their composition, but otherwise, if they are not, they would be treated anyway as a multi-component material, because we are afraid that still there is the idea that people can think that if each component is tested as good, okay, so the object is good, but this is not always the case. As I try to convey this message, we cannot rely only on single components. So you have to assess the multi-component object as a whole, and the total risk of false decision is not equal simply to some kind of combination of the singular risk for the singular components, unless we are under the hypothesis of independence, but I don't enter here the detail. I mean, every multi-component object should be analyzed in the appropriate multivariate context with a special attention to the compositional nature if it is a compositional object. So I think that investigating the vaccine, thank you for the suggestion, would be sure very interesting and important nowadays. Thank you.
Yeah, thank you very much.
Thanks, Francesca. Thanks again. So I will move to the second paper, and I will try to share again my screen. Here it is. So efficient experimental design is critical for achieving fit for purpose measurement results with the aim of not to waste precious resources. This is particularly true when a laboratory has to deal with a completely new measurement procedure. This paper, Optimizing Experiment Design for Chemical Measurements, presents a statistical experiment design procedure for a typical two-phase experiment for quantitative chemical analysis. As a specific case, a full example of an experiment design applied to isotope dilution LCMS is presented, which has been designed by using the specific NIST application Abacus. The speaker is Dr. Toman from NIST, the National Metrology Institute of the United States. Please, Blaisa, the floor is yours.
Thank you very much. I'm not, yes, there I am. Okay, I wasn't sure I was on screen. Thank you very much. I'll share my screen. Oh, oops, that's not it. Let's see. Oops. Okay. Okay. Thank you very much. I very much appreciate us receiving this award. It was a great surprise and a great pleasure for us to get this award. And I'm happy to give this presentation. My work is together with Mike Nelson, who's a chemist at NIST and has been my longtime collaborator on this work, and also Yang Ma, who's a graduate student, now has received his degree, but he's been working with us on a lot of the programming. Let's see. Okay.
Very sorry for interrupting you.
Yes.
What we see is the presenter's mode.
Oh, I'm sorry. Okay, I have two screens and I'm not sure. Let's see. Okay, this. Let's see. Okay, maybe. I don't know. Let's see. Do you know where I can find the? That's not it. Sorry.
Yeah, I think you should have the possibility to choose a specific window.
Okay.
Click on the window, on the specific window you want to show when you have multiple screens.
Okay. Let's see. No, that's not it. I'm sorry.
Blaza, excuse me, Francesca speaking. You
Yes.
go to display setting on the top.
Display setting.
Yes, try that.
Okay. Okay. Oh, presenter.
Try
Okay, yes.
yeah.
This, okay. Is that it?
Good.
Yes, okay. Sorry about that. Okay, so what I'm talking about and what our paper's on is this essentially designing experimental designs for a specific chemistry application, but it's one that for me at NIST has been a very common question over the years. And when someone starts a new experiment, they would always ask me, you know, how many measurements of this should I have? How many measurements of that? And so on. So at one point when we had worked out our Abacus app for the analysis and uncertainty analysis of the data, we decided to go for trying to come up with an app for the design part of the experiment. And so it's usually the responsibility of the chemists to actually construct their measurement schemes and to achieve the confidence, but they would ask the statisticians to guide them in this. And so what I'm describing here is essentially a method that we came up with and the automated app that they can use now to use it themselves. So it's a very specific experiment. It's a two-phased experiment, which has a calibration part, which establishes the relationship between the known quantities of the analyte and the corresponding responses on the chemical detector. And the second phase is when you actually use the calibration function to estimate the unknown based on essentially the same instrument. And so it interprets the result, the measurements from the instrument as to get your final answer. So an example is the determination of mass fraction of an analyte species through the IDLC-MS instrument and using an internal standard. So that's why we have these ratios here. The basic methodology can be applied to essentially any two-part experiment of its kind, but this is what we have, what we are using it for mostly at NIST. So we have the X and the Y axis. You have this is for the calibration experiment. You have your essentially known ratios on the X axis, and then you have your response ratios on the Y axis. In this case, we use 5 calibrants, so there's 5 points, pretty well fitting a line. And then the second experiment simply uses the line to get from a Y to an X. So this is a very common thing I'm sure you're all very familiar with. And what we did then was write some, software that will do this design for you automatically. So experimental design consists essentially of a number of measurements and also where do you take the measurements on the X-axis. So in this case, the calibration experiment has how many calibrants do you want to use? What's the number of the replicates? How many times should you measure for each calibrant? And then where do you measure on the X-axis? So those are the parts of the experimental design for the calibration experiment. For the quantitation experiment, it's simpler. We only have how many samples of the unknown do you want to use, and then how many replicates per sample do you want to measure. And, you know, as everyone knows, when you do experimental experiments and you calculate your uncertainty, the more measurements, the better. So we need some sort of constraint. And so we have a constraint on the total number of measurements. But also we want to achieve a certain maximum expected relative standard deviation for the measurement, the measurand, sorry. So those are the two constraints that under which we optimize. And because this is not a simple process, what we end up doing is finding locally optimal designs, not, you know, because the design will depend on unknown parameters, because experimental design is a pre-data situation, so you don't really have all the information. So a lot of it has to be obtained. Some of the information that you need to come up with a good design has to be supplied either through small prior experiments or some other ways, maybe expert opinion of the chemist. So here's the schematic of the experiment with 3 controls measured twice, calibrants, not controls, calibrants measured twice, and then 2 samples of the unknown measured 3 times. So you see how it flows through the 2 experiments. You have the calibration function estimated in the middle, and then you come up with the final answer, which essentially you're looking for the W of the fraction of the unknown there in the ratio. So I'm just going to give a little bit of the statistical modeling because it maybe would be boring, but if you're interested in that, it's in the paper in Metrologia in greater detail. But the main part of this is that we have in the calibration part, we do use a linear calibration here. So that's something you have to check, you know, before that your data is going to be good for that. Most of the stuff that we see at NIST does fit these linear calibration curves, but once in a while you will need something else, and in that case, this won't work. But here we have a linear calibration curve. You can see that it's just a regular regression, but what makes it slightly different is that we have error in the x variable, because, you know, we have our response, we have our x measurements and essentially our y responses both have uncertainty. So that's why this is a errors in variables type regression, or you can say generalized distance regression, but it's, you know, it's a modification of just linear regression. And in the first experiment, the goal is to estimate the slope and the intercept and the covariance matrix, and then carry that through to the next experiment, which is the quantitation. And here you use the same calibration curve. Now you will observe a y, and you're looking for essentially the expected value of the x. And what we'll have to end up supplying is some variances, or you can think of them as uncertainties, which will be the heterogeneity of this material that you're using, and also the variance of the response. So here the goal is going to be to obtain the estimate of the variance covariance matrix, or variance. At this point, it's going to be variance because we have a scalar quantity of the estimate of the measurand. And you know, after we have this formula, we can then optimize it, which is we find the optimal design, which is this set of these numbers that will minimize that variance. So I just stuck in here the formulas just to see what that, it's fairly complicated. The red parts are the parameter values we have to supply somehow. The blue parts are what this is continuation of that variance. The blue parts are what makes up the experimental design. So at this point, we can say a few things about general things about the experimental design based on, say, the variance of the X, the fraction of the mass fraction. If you can measure, if you think that the uncertainty there is constant in absolute terms, which means, across the x-axis, it stays constant, then the design will tell you to have as many standards as possible and measure them once. So this is what comes out of the optimization. If, on the other hand, the variance or the uncertainty in the X is constant in relative terms, which is that as it increases, as you go and increase that, the variance increases proportionally to the size, then you will have fewer standards and you will be measuring them more than once. And for just about everything I see that the data that I have analyzed, that is actually what's happening. So having a constant variance for the X absolutely across the x-axis hardly ever happens. So you would generally be better off specifying the variance or the uncertainty in relative terms. And the sizes of the calibration and quantitation experiments will depend really on the sizes of these various variances. So since we're specifying a total size of measurement, then how it's allocated will depend on these uncertainties. So the actual optimal design for a specific situation, you will just do it numerically. So that's why we have this Abacus app. It does the optimization under these constraints I already mentioned. And it uses it's pretty much a search, but it does reduce the set of possible designs to a certain smaller set than just like all possible designs based on some known results from optimal design about balance designs and things like that. But it's basically a search over a set of designs. Just to kind of tell you a little bit about what our Abacus looks like. This is the package that we have produced. It has several now, even more modules than are listed here. So here we have 4 modules, the white boxes. And we had started with the linear regression analysis box. That's what really we wanted for the chemists to be able to do their own uncertainty analysis. And then we expanded that to having response factor analysis. And then we added the design of experiment module, which uses there is a pre-analysis, so something that will produce the estimates for the inputs that you need into the design of experiment package. And so you can imagine doing this procedure where you do a preliminary experiment, produce some data, feed it into the linear regression part, then that feeds the design of experiment part, then you do your experiment, and then you feed it into the linear regression analysis and produce your answer. So that's our goal, and we have been able to, we have started on that. We'll definitely have people using the analysis packages. We are still just kind of starting in the design of experiment packages use. So here's one of the screens. Sorry, that's not a particularly great view, but it's from a screenshot. And you can see how you tell it the maximum number of measurements, the maximum relative % standard uncertainty that you would like. And then the uncertainty values or the variance values are given as ranges. So you can say, well, I think my range of the uncertainty in a peak areas is, you know, those two numbers that are circled. So you don't have to have like a specific, you know, particular number, but you have to know a range of possible numbers that you could have. And after you put, you know, fill that in, then you just hit the key there and it will produce the design. So the key question, of course, is where do you get the input values? Because they're very specific things that don't look like that would be that easy to come up with. And so in the article that in Metrologia, we have a worked example of a pre-experiment that measures the 25-OHD3 in serum mass fraction. So here's just so you can see some of the data that goes in. It's not, there's mass of the internal standard, mass of the analog, and so on. So just the idea that these are the kind of data that goes into the abacus from the calibration experiment. This goes in there from the quantification experiment. And then it produces the actual results that you can then feed into the design of experiment package. So I label them here with the corresponding symbols that are on the other slide that has the statistical model. So, and then when you do that, you produce your experimental design, and you can see here it says that the number of calibrants is 6 and the 2 measured twice, and then you should have 10 samples measured once, and that it will produce, also tells you where to place those. And the expected relative % standard uncertainty here is 3.48 because we asked for 3.5. And since it's only 22 measurements and we said we could use up to 40, you can say, well, maybe I could do a little better than 3.5%. So you can rerun your design of experiments with requesting a lower standard uncertainty and see what happens. And here we requested 2.5% with 40, total 40 of measurements. And you can see it at that point, it says, it gives you the optimal design, but then it says it's 2.57, you requested 2.5. So if you want to really get 2.5, you have to increase your number of measurements. So that's essentially it. I don't know how I did on time, but the idea here was that we would produce an optimal experimental design for a common type of chemical experiment. And we would either need to have expert opinion for those uncertainties, or more likely do some smallish experiment with the same kind of data and produce the values that we need for the design, and then, you know, run our a design of experiment app and produce the experiment. And then if you do that, then the results from the actual experiment that you do are likely to produce the relative standard uncertainty that you require with the smallest number of measurements that you can do. So that was our goal, and with testing that we have done, we seem to be meeting those goals. So thank you very much, and I will take questions.
Thank you so much, Blaise, for your presentation. Are there questions or comments? I don't see anything in the chat. Francesca is asking if would there be, or will there be, sorry, in the app the possibility to use other regression functions, not only the linear one.
Right. So the idea, yes, we have to basically have another module, in our suite of apps, because the design is very specific to the linear regression. So yes, it's possible, but it's not like a very flexible thing where you can just feed in your calibration curve and then get the design. So it's not really set up for that. I don't really expect that we will have that. We might have something where we might make it, let's say, more of a polynomial function, but I don't know if we're gonna, have the request for that. This whole Abacus suite is kind of meant for people that it's meant for the chemists that do kind of semi-routine measurements. They're SRM measurements, but they're not like brand new experiments and so on. So that's really what it was meant for, and I think that's kind of where it's going to stay. So
thanks. Is there also there is also a question from Zoltan asking if these apps are available on the NIST website?
Yeah, so we have, we can give them out, and we're working on having it, we have it internally, and we're still working on having it externally because, it's all the security issues are kind of difficult for people to get permission to do that. So we are in the process of getting that permission and having it externally facing. But at this point, if anyone wants the app, we can actually give it to them. It's in our Shiny package, so it's not something that's very difficult to install on your own computer.
Thank you so much. I hope that you will be advertised to the community when they will be available on your site.
Okay, sure. Thank you so much.
At least passing through CITAC. Thank you so much.
Thank you.
Yeah.
Thank you so much.
Other questions or comments? If not, thanks again. Thanks again for your presentation. Thank you. And we can move further to the third speaker. Okay. I will try to share my last slide. So we have the third paper that has been awarded with the title Quantification of Single-Strand DNA by Sequence-Specific Counting in Capillary Flow Cytometry. The quantification of DNA can be carried out by means of different methods, and each method uses a different measurement principle and thus shows particular intrinsic strength or weaknesses in application to specific biological samples. Therefore, the most appropriate method for DNA quantification must be selected according to the purpose of the analysis and according to the properties of the samples to be analyzed. The present paper reports an approach to achieve sequence-specific counting of single DNA molecules, which is required for versatile applications. The direct counting of individual molecules has a potential for substantial reduction of measurement uncertainty due to its straightforward measurement principle. The speaker, one of the authors, is Dr. In-Chul Yang from KRIS, the Korean NMI of Korea situated in Daejeon. Please, In-Chul, the floor is yours.
Thank you very much for the introduction, and I am honored and proud that our paper was selected as one of the best papers, CITAC best papers, and thank you very much for giving me the opportunity to introduce our work on sequence-specific counting. Sequence-specific counting of single-strand DNA in capillary flow cytometry. Okay, my presentation will cover introduction, DNA counting history, and sequence-specific counting of DNA and sequence-specific counting of RNA. About 15 years ago, we planned a potential strategy for establishment biometrology. We classified biological substances into several different categories based on their physical and chemical natures. First one is large and discrete. Cell, virus, and DNA and RNA belong to this category. We wanted to quantify this category based on counting using flow cytometry or microscopy. And second group is polymeric and stoichiometric biological substances. They are DNA, protein, and sugars. They are complex, but we can break down the complex and big molecules into simple and regular building blocks. Then we can quantify the building blocks or elements based on well-established chemical approaches such as elemental analysis or IDMS. The third group is complex and implicit properties such as activity, viability, and cellular reactions. For these complex properties, we wanted to apply best practice and standardization approaches based on parameter optimization and so on. And now we have a new measurement categories termed non-canonical measurements, including sequence, identity, and population properties. I think we need technology innovation for measurement of these properties. So my talk will be on the counting of DNA molecules in this approach. Our system for DNA counting is very simple. Sample here will be injected into capillary, and the molecules passing through the detection window will be visualized and counted. We built the instrumentation by ourselves at KRIS. DNA molecules passing through the window was visualized like this and counted in oscilloscope. In 2009, we first reported proof of concept for lambda DNA by counting individual DNA molecules. This figure shows the lambda virus, and 47 kilobase long DNA is in the head of lambda virus. The virus itself, viral DNA itself is not fluorescent. if we add fluorescent dye such as cyber gold or cyber green, then the dye make a complex with DNA and become strongly fluorescent. But free cyber green dyes are not very highly fluorescent because fluorescence easily and readily quenched by water molecules. So if we add cyber green dyes into DNA sample, we can visualize and count these DNA molecules. Okay, so we count the lambda DNA molecules by counting, and first published our results in Metrologia in 2009. After 5 years from the reporting of lambda DNA counting, we reported counting of plasmid DNA. Plasmid DNA is only 4.4 kilobase long. Its length is about 10 times smaller than the lambda virus, and fluorescence intensity is proportionally lower than the lambda virus. So we needed to improve our optical systems and data processing procedures. Okay, and at that stage, we were concerned with accurate quantification. For assignment of accurate values, we needed to accurately measure the sample volume. So we applied 4 different approaches to determine the sample volume: fluorescence, weighing, and SEM imaging, and manufacturer's information. 4 values were highly equivalent to each other, and we report that our approach is very accurate, and we suggest our counting approach as a candidate reference method for quantification of plasmid DNA in Metrologia in 2014. Based on the successful quantification of plasmid DNA, we organized the international comparison study for quantification of plasmid DNA, SysQM P154. The study was to compare digital PCR approaches with counting approach for quantification of plasmid DNA. Participants and their methodologies are summarized here, and reference values were determined from 4 different methods: counting, digital PCR, and IDMS, and CE analysis. They are highly equivalent, and the participants' results are shown here. They are not very highly equivalent, but I think it's okay because it was the first comparison about the absolute quantification of DNA molecules. Absolute quantification means the results were not calibrated by any reference materials. So we reported these results in analytical chemistry in 2016, and we also reported our approach for quantification of supercoiled plasmid DNA based on bilateral comparison with NIM China in 2015. Okay. Results in the previous slides were sequence non-specific counting. DNA molecules were stained with the fluorescence regardless of sequence context and then counted. However, many scientists in biology and healthcare and food industry are more interested in quantification of specific genes, not the whole DNA contents. So at this stage, we wanted to advance to the next step: sequence-specific counting and quantification of specific target genes. For successful sequence-specific counting, we had to consider many new parameters, such as selection of target nucleic acids, design of sequence-specific probes, and hybridization conditions, signal intensity and signal-to-noise ratios, and impurities in size and sequence context. And And we were concerned how we can validate our approach or our results. Our goal was to accurately quantify specific target molecules. Two things are important in our goal. One is not to include incorrect or noise signals. The other is not to miss correct targets. We wanted to validate if we are counting or including incorrect or noise signals by testing many negative controls. And we want to validate our results by comparison with the other quantification methods. Okay. First, we optimized probe numbers. This is the M13 single-strand target DNA. M13 is naturally single-strand DNA. It is purchasable from commercial companies, and it's very good for our approaches because it is already single-strand DNA, and we does not require any artificial denaturation steps for hybridization of sequence-specific probes. We used fluorescently labeled sequence-specific probes. They can be synthesized from commercial companies, but the price of synthesis is more than $100 per probe. So it is better to use as small number of probes as long as the counting quality is maintained. We test 10 to 40 probes in this region, and we select the 30 probes conditions for the final measurement. It is stable enough and more economic than the 40 probes. So we select a 30 probes condition for the counting, and we test repeatability of 18 measurements from 6 independently prepared samples. After optimization of probe numbers, we tested many negative controls to rule out the possibility of inclusion of noise or incorrect targets. Negative controls are buffer blank, no DNA and no probes controlled. In this sample, target is absent, and incorrect fluorescent probes. And fluorescent probes only. In this sample, no target DNA is present in this sample, so we expect virtually no signals in these negative samples. The results are shown here. Very low signals obtained from the negative controls compared with the correct sample. And the negative signals in the negative samples were not due to absence of target DNA molecules in the sample. If we add sequence non-specific dye in this negative sample, these signals are highly fluorescent because some DNAs are really present in those negative samples. So they were not counted not because due to absence of target DNAs, but due to lack of certain essential components for successful hybridization. Next was optimization of hybridization condition. We used the PCR buffer for hybridization, but the value was very low compared with the calculated value based on UV spectrophotometry. So we changed our buffer system to a commercial hybridization buffer, and we optimized the concentration of the hybridization buffer to 40%. And the other was we also optimized the concentration of target DNA and probe concentrations. If we use very low concentration of target DNA or probes, the signals are very, very low. It was because DNA probes in low concentration had very low chances, no opportunities to collide with correct targets. So hybridization in very high concentration was needed for successful counting. After hybridization, we diluted the sample by 300,000 folds for counting. This was further illustrated in this slide. We wanted to maintain the signal to noise ratio over 3, more than 3. If we are focusing about 10 micrometer dimension in the capillary, the target DNA molecule will have 30 flow poles because 30 probes were hybridized in this target DNA. Then free probes in this area should be less than 10 free probes should be present in this area to maintain the signal to noise ratio of 3. If we use sufficiently low concentration of target DNA probes, virtually no signals was obtained in this approach. So we changed our strategy to use very hybridization in high concentration and sufficiently dilute the sample for counting. We had to remove these free probes to because these free probes will produce noise signals. If these free probes are not removed, the true signals will be buried in the noise signals. So first we used filtration to remove these free probes, but the filtration resulted in loss of target DNA. Next was to treat with nuclease to remove these free probes, but it also resulted in loss of target DNA. So we used to dilute this sample to maintain the free probe concentration very low, not detectable in this focus. So the sample was diluted by 300,000 folds for counting. This slide shows the raw data from plasmid DNA and from M13 sequence specific counting. You can see photon count here about 40. And it is the signal is very high and very clearly separate from noise signals here. However, for M13 DNA, the signals, correct signals are here. They produce about 4 photons in 100 microsecond intervals, and noise signals are about 1 photons per 100 microsecond intervals. So the positive signals are not very easily separated from noise signals. So we need further signal and data processing for this data. Okay, the photon counts were collected for buffer blank and for buffer blank in black and for probes only control in red. And true signals from hybridized M13 samples in blue. You can see new signals in the hybrid sample. These signals represent correctly hybridized M13 DNA. However, the signals are highly overlapping, and we apply the cutoff threshold here to remove all the noise signals from buffer blank. Then the signals became like this. This signal is from hybrid sample, and this signal is from probes only control. It is also, this slide also represents noise signals from probes only control. So we subtract these signals from the hybrid sample, and leading to blue open square signal here. It represents a nice Gaussian shape and represent molecular counts of M13 DNA. Okay. For successful counting, we optimize probe numbers, hybridization conditions, and concentration of target DNA probes. We also optimized data processing. Now we wanted to validate the accuracy of our results by comparing with other methods. We compared our results by counting with results from digital PCR approaches and IDMS and UV. The final results are shown here. Sequence-specific counting and digital PCR for region 1 and digital PCR for region 2. They are very highly equivalent to each other. And the results by IDMS and UV are shown here. They are equivalent to each other, but the results are different from counting dPCR and dPCR2. Please note that these three approaches, counting, digital PCR, are sequence-specific methods. However, IDMS and UV are sequence non-specific methods. Let's assume a sample with a correct DNA with long length and middle length and very short length. And incorrect DNA impurities are present in the sample. They are different genes, so it should not be measured or counted. And some RNA can be present in the sample. If we measure this sample by counting, our counting approach will count only this target. Correct, very long sequence with correct sequence. PCR technology will quantify this long target and middle-sized target if the size is more than 100 base pair. Counting and PCR will not measure and quantify this incorrect target and RNA. However, mass spectrometry will measure all the DNA species regardless of size and regardless of sequence context. And further, UV will measure all the nucleic acid species. So if sample is pure, highly pure enough, if sample is not highly pure enough, the 4 different methodologies could result in different values. So we wanted to explain this disagreement between sequence-specific methods and sequence non-specific methods based on the impurities in terms of size and sequence. Next is counting of RNA. We select MS2 RNA virus as a model system. MS2 RNA is about 3.6 kilobase. We designed probes here and here in two different regions. And we optimized hybrid condition in terms of probe concentration, in terms of molecular distances, and number of probes and denaturation temperatures. You can see we need 70 probes for successful and efficient counting of RNA molecules. Please remember, we used only 30 probes for counting of M13 DNA. However, we need 70 probes for counting of RNA. We don't know why we need more probes for successful counting of RNA. However, it can be explained by the difference of size. M13 DNA was about 7 kilobase long, and this MS2 RNA is about 3.6 kilobase long. The size is about twice. And the other is very complex secondary structure of RNA. It is well known that RNA can form very complex secondary structure interfering with hybridization of probes. So we thought that the requirement of much more number of probes is due to size or due to secondary structure. And this slide shows the final results for MS2 RNA. This is from sequence-specific counting, and these two results are from the reverse transcription mediated digital PCR 1 and 2, and from UV. The counting results were about 30% higher than the results from digital PCR technologies, but about 20% lower than the value by UV spectrophotometry. We thought that this difference, the higher values than the reverse transcription digital PCR, was due to reverse transcription step. The efficiency of reverse transcription is not 100%. So this difference was due to reverse transcription step, and the lower value by than the UV is due to, we thought, is due to some fragments and sequence impurities in the RNA sample. Okay, so in conclusion, we demonstrate sequence-specific counting for single-strand DNA and single-strand RNA. Now we are applying our method for quantification of HIV RNA and quantification of coronaviral RNA. Second, the counting and digital PCR produced the very highly equivalent quantities for single-strand DNA. However, for counting of MS2 RNA, counting produced a much higher value than the digital PCR because it was due to reverse transcription, inefficient, incomplete reverse transcription efficiency. So we think the quantification by counting is better, could be better, because it does not require the reverse transcription step. And we think counting strategy is linking biological quantities directly to definition of mole, number of molecules. So we hope in the future we could realize more traceable measurement of DNA, RNA, virus, and protein in the future. Okay, and Dr. Sang-Yeol Park was actually conceptualized this study, and he did most of the instrumentation and supervising. However, he was acting as a general director of quiz, so I temporarily supervised this project for 3 years. And Dr. Hee-Bong Yu was doing experimentation, troubleshooting, and data processing. Dr. Ki-seok Hong was responsible for the optics and data processing, and Ms. Chaeun Lee performed digital PCR and IDMS. Okay, this is the end. Thank you very much.
Thank you so much for your very interesting presentation. Thanks. Which particularly in this pandemic moment sounds really great for the new possibilities these techniques could open. Do you see any applications in a short time framework of this new method for the addressing specifically the COVID-19 virus?
Actually, we are applying our method to quantify coronaviral RNA in this. We produced reference materials of coronaviral RNA, but based on reverse transcription digital PCR technology. We think the value is not very traceable to the definition of mole because it is relying on reverse transcription step. So we are testing the accuracy of the digital PCR based methodologies with our counting approach, and we also applying our approach for direct counting of virus particles, coronaviral particles. However, we have some technical difficulties in counting viral particles. They are very dispersed in the capillary. They are not focused in the center of capillary. So we think we are missing many true virus particles in our counting.
Thanks. I have a question from Bernd. If we understand correctly, you assume a systematic bias in the digital PCR measurements. Is this correct?
I think there is no significant systematic bias for quantification of DNA, but for quantification of RNA, it relies on, it is mediated by reverse transcription, and the reverse transcription efficiency is generally known that it is not 100%. It's about 50 to 100% in some values. So it is systematically biased. I think reverse transcription mediated digital PCR technology will produce systematically underestimated values of RNA. It is my opinion, my point.
Thank you. Are there other questions? I don't see anything in the chat. If not, thanks again. Thanks to all the three speakers, and I think it was great to have 3 different papers like these ones on different topics and from 3 different continents. This was a great success from this particular edition of the award. I will give back the floor to Bernd for the closing remarks.
Yeah, thank you very much, Michela, for your presentational work this afternoon. So I can only agree with your assumption and your conclusion that we have had 3 excellent papers from very different areas, subject-wise and geographically. And I think this is a very good indication for the global appearance and activity of CITAC, and this is very valuable to all of us. And although these different contributions come from very different subject fields, it is very exciting to see that important questions of metrology and chemistry are in all these areas very present. And I think especially the last topic is something that is something which is very well suited for further research in conjunction with the CCQM, and an extremely important topic in these days. And there's really a lot of work to do for all of us. So it is very, very nice to see and very exciting that all of you are very active in this very present fields and in this probably most important topic in metrology altogether. So this is an exciting time. It is also a time which is not only dangerous for our health, but is also scientifically very exciting to see how developments go. And I think it is good to see that science has something to contribute to a solution to the current problem. So this is very encouraging. And I think that's what we can take away as a take-home message today, that it is very well worth working in metrology and chemistry these days. So thank you very much to all your exciting contributions. Congratulations to your awards. You really deserve it. So that is very exciting for us. And no matter as to whether we will be pandemic in the next year or not, I think we will continue with this kind of frame of having these seminars as web seminars also in the coming years, and a real improvement on our work and our public relation to everyone else. So thank you all very, very much for all your things, all contributions, and have a good work, have a good time, and more of all, stay healthy. All the best to all of you. Bye-bye.
Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye.